Hello, my name is Forbes Walker. I'm the Environmental Soil Specialist with the University of Tennessee Extension. And today with my colleague, Dr. Neil Aish, we're going to be talking about some of the basics of soils. It's very important if we want to understand soil health, we've got to understand something about how soils are formed, what properties they have, what is important in a good functioning soil. Dr. Aish teaches this course over a semester here in Knoxville, Introductory Soils. We're going to try and do this in about 20 minutes, so let's get started. So this is an overview of my presentation. I'm going to be talking with some definitions of what a soil is, and then discuss some of the soil forming factors that are important. Then talk a little bit about some soil physics, about the influence of soil particles on soil structure and how that influences soil water and water management. Then talk about the minerals and the clay components of the soil. And then talk about the nutrients that we find in the soil that are important for plant growth, as well as soil pH, and how we might amend these nutrients and the pH with different amendments. We will briefly talk about what the definition of soil health. I'm really not talking about biology much in this presentation, as the presentation following this from Jen de Bruin will be talking in much greater depth about the wonders of soil biology. The figure we've got here on the right of the screen is a typical screen that is typical schematic of what a soil profile looks like. You will find throughout a soil different profiles with different characteristics. You can see in this particular example, we've got a lot of organic matter in the top, in the O and the A horizon. Not much of us moving beyond the A horizon, but in the B horizon, we'll see a lot of clay accumulation. So this is a common thing, that a soil is not uniform. You'll have different horizons, and these horizons have different physical and chemical properties. So what is a soil? So a soil is the unconsolidated mineral and organic material that we find on the surface of the earth. It's generally, will support plant growth. And what do plants need to grow? They need nutrients, they need water, and they need a place for anchoring their roots and for the gaseous exchange between the roots and the soil. Soils are also very important for water infiltration and storage, and so that's really what is in good definition of a soil for us soil scientists. Engineers, on the other hand, have a different view of soils, and they're often looking at a stable medium on which to build roads or buildings on. So they're interested in how the soils change properties when they get wet, or when we've got more or less of certain textures, clays or sands in there. And a final thing, which is really what the purpose of this whole tour on soil health is about, is understanding how we can improve and manage the soils as a habitat for soil microbes. Typical soil in Tennessee, it's very difficult to say what a typical soil is. There's so many different types of soils in Tennessee, but generally, about half of a soil, we want to see about half of it made up of mineral and organic fractions, and the other half with void spaces or pores. In Tennessee, it's very difficult for us to get our organic matter above much higher than 3 or 4% because of being in the humid southeast. It's very quickly decomposed. So for our mineral and organic fraction, most of it's going to be the mineral fraction in Tennessee, with the small part 3% organic. The pores and the voids that we like to see are going to be about, we like to see about half of them filled with water and about half of them filled with air. Obviously, if there's less water, it's going to be difficult for the plants to access the water to grow well. And similarly, if there's too much water, there's not going to be enough air, and that can lead to problems as well. So it's our typical type of soil. Let's talk briefly about soil forming factors. The parent material on which the soils are formed, the climate, the organisms, the landscape position, and the time are all very important. We look at the couple of slides, the photographs we've got a picture of the Smoky Mountains in eastern Tennessee here, and a picture of a soybean field at the Milan Research and Education Center in West Tennessee. Quite different parent materials, very similar climates in those things, somewhat different organisms, and quite different landscape positions. So we have different soils in these things. We think about the parent material. Parent material in the eastern part of the state is very much driven by the geology, and the geology is dominated by a landscape, limestone materials. So that's what helps form our soils East Tennessee. West Tennessee, we are few thousands of years ago, we had lots of deposits of loess or wind-blown materials that came in from the north, and they very much dominate how the soils that we find in West Tennessee. Climate and the climate is important for the way how fast the soils form, how weathered they are, and it's the rainfall and the temperature that we typically are interested in. Temperature obviously helps drive the rate of chemical reactions, as does water and rainfall. The organisms under which these soils are developed and develop are very important. You know, are the soils developed under a grassland or a forest? Obviously, in the Smokies, we've got dominated by forests. These are forest type soils we're looking at in a lot of East Tennessee. Whereas grassland, if we went to the Midwest, we'll see a lot of our soils developed on grassland. And the interaction of the grazers on these grasslands over the millennia are very, very important. I'm not going to talk much about soil microbiology in this talk, but also the microbes, the bacteria, the fungi, the viruses that we find in the soil are always very important. The landscape position is very important. Obviously, if we've got a soil on the side slope in the Smokies, we're going to have a whole lot of erosion going on. So while the soils at the top of the slope or the bottom of the slope may be relatively old, the ones at the side slopes are constantly eroding and they're constantly having to form. So these might be quite young soils, whereas if we go to West Tennessee, a relatively flat topography, erosion is going to be much less. And that obviously influences the age of the soils. Switch gears quickly, let's talk about some soil physical properties. The soils, as we mentioned, are dominated by a number of mineral particles, and these are all going to have, as well as organic materials. These are going to have different densities. So the density of the mass per unit volume of organic materials is much, much less, the order of less than 1 gram per cubic centimeter, compared with some of the minerals that we find, which typically are in the range of 2 to 5 grams per cubic centimeter, with the dominance of the around 2.65 grams per cubic centimeter. The densities of these individual particles is not as important as a term we call the bulk density, which measures the mass of the soil, which includes the pores and the spaces for air and water. Typically, we like to see, as we mentioned earlier, about half of the soil to be made up of these pores. We want a good distribution of larger pores and small pores, kind of 50-50 mix. The large pores are obviously very important for draining the water, whereas the small or micropores are very good at holding the water and making that water available to plants after it has rained. For a good soil, a good bulk density, we're looking at around 1.3, 1.4 grams per cubic centimeter. Again, that's capturing the pore spaces and as well as the mineral and the organic fractions. The bulk density is going to, depending on the dominant texture, whether it's a sandy dominated soil or a silt or a clay size thing. Typically, the texture is going to be important in that the surface area of individual particles is going to determine how many pores and what size pores we got. Typically, if we've got a lot of clay in the soil, we're going to have large amount of surface area, and we're going to have a lot of finer pores in a clay soil than in a sandy soil. While the texture is really important, what we're really interested in is how do these soils aggregate and form the structure of the soil. And the structure is going to change with depth with these different horizons we talked about earlier, with the amount of organic matter, the amount of how well drained the material is, as well as the traffic that we see. This is a textural triangle that the United States Department of Agriculture comes out. If you know the percent of sand, silt, and clay, you can find out what kind of soil you've got. Basically, as we mentioned, texture is important, but it's really the soil structure that we're really interested in. And this is the 6 basic types of structure, from granular, which is the organically rich crumb-like particles that we see on the surface of some soils, to blocky. This is typically what we see in most of our soils in Tennessee, where we took a bit of soil out, we come up with a little block of soils. Platy structures, we do find these in some parts, especially where we have fluctuating water tables close to the streams and rivers. We see these things. These other structures, the massive structuralist and the prism or columnar, not so important for our soils in Tennessee, although they are important in other parts of the world. Color is a really great indicator of many soil properties. If we got a soil that's dark, black, we typically suggest that we've got a lot of organic matter. If we got a lot of soils that are reds or browns or yellows, typically as we do have in Tennessee, that tells us that we have a fairly well drained soil. The color from the reds, the browns and the yellows comes from iron. There's a picture on the side of a range of the different colors we see in their soils in Tennessee from our soil test lab. If that soil is saturated for long periods of time, the type of iron we see in the soil changes, and so the color changes. And so we typically will see a grayish soil, which indicates that there's poor drainage conditions and the soil is saturated for a lot of the time. In other parts of the country, if we have some white deposits in the soil or whitish soil, that's often an indicator of a high silica content soil or with salts. Quickly talk about the minerals. So the minerals are often the parent materials that from the original geology of the area. So if we remember back to our introductory geology, primary materials can either be igneous, i.e. coming from volcanoes, metamorphic or sedimentary. These are basically rocks that are made up of a bunch of chemicals, a bunch of minerals, and they're not chemically altered. Over time, with the influences of climate and different things, these minerals will start to dissolve and break down into their constituent nutrient components and then form secondary minerals. These are often known as soil colloids or clays. Our clays in Tennessee are dominated by aluminosilicates, which have got a lot of iron as well as aluminum in them. They're really important because of the high surface area they have, as well as the negative charge associated. We do have deposits of certain salts, calcitic and dolomitic limestone, as well as gypsum. So we've got a soil with some organic materials, and these are the stable organic matter, or the humus that's left after the decomposition of plants and animals, tends to be very dark brown or black, relatively insoluble in water. Important thing about the humus of the soil or the organic colloids there is it typically has a very high negative charge, and this negative charge tells us how good that soil is going to be at holding certain nutrients. It also, organic matter will add a lot of water holding capacity, and if you start to build up your humic content or your organic matter content in your soils, then the organic matter content starts to really be very important in the types of soil you have and the materials. This thing is called cation exchange capacity. It's a measure of the charge associated with the soil, and it's very important for holding certain nutrients like ammonia, the ammonium form of nitrogen here, potassium, calcium, and magnesium into the soil so we don't lose them. And if we have soils with low cation exchange capacity, which many of our soils are, because of the nature of the types of clays we have, the organic matter becomes much more important. Soil fertility is the capacity of the soil to produce the desired crops by supplying the essential nutrients. So essential nutrients, we've got them listed here: carbon, hydrogen, oxygen. They're obviously coming from the atmosphere and from rainfall, CO2 and H2O. In the soils, the plants, we break our nutrients down into primary nutrients: nitrogen, phosphorus, and potassium. These are the nutrients that the plants need most of. Then the secondary nutrients: calcium, magnesium, and sulfur. We need them in relatively large quantities, but not as, and then the final group of the micronutrients, the coppers, the borons, the zincs, etc. We need these in relatively small quantities. These are often mediating enzyme activities in the soil. If a nutrient becomes limiting in a soil, it's going to limit plant growth. So this is where we pay attention to what our P and K levels are. If we start to see that these nutrients becoming deficient, we may need to add them in terms of amendments as fertilizers. Soil pH, we'll talk a little bit about soil pH. Soil pH is a very important measure of soil. It's a measure of the concentration of hydrogen ions. pH is typically on a 1 to 14 scale. It's a logarithmic scale, which means the hydrogen ion concentration from 3 to 4 is a tenfold difference rather than just a linear doubling. Most crops, we need a pH of between 5.7 and 6.5. And it's really important that we maintain it around there. Not so much for the hydrogen ions, but really what happens with under these low pH conditions, because our soils are dominated by aluminum, aluminum becomes soluble and is toxic at a low pH. So we were trying to keep our pH at above 5.5, which is where we come up with the recommendation 5.7 to 6.5. How do we correct it? We correct it with limestone, and we determine this with a soil test. Quickly talk about fertilizers and fertilizer analysis. This is an example of a blended fertilizer, a 5-20-20. What does that 5 mean? The 5 means it's a 5% nitrogen content in the fertilizer. The 20 refers to the amount of phosphorus as P2O5. It's not the elemental P, but it's this P2O5 form of phosphorus. And the last number is also refers to the potassium or the potash. And again, this is reported as K2O. These P2O5 and K2O don't actually exist in nature, but this numbering system still continues to this day. So that's how we look at our phosphorus, our commercial fertilizers. Mentioned we do have quite a lot of certain organic materials that can be used as alternative fertilizers, broiler litter being one of them. We have a lot of broilers grown in the southeastern United States. We estimate in Tennessee 200,000 tons of broiler litter. Typically a ton of litter is going to contain about 60 pounds of nitrogen, 50 pounds of phosphorus as P2O5, and a similar quantity of potassium as K2O. So it's like a 3-3-3 or a 2.5 fertilizer. One of the things we'll always recommend about soil testing is really important to take a representative sample and have it analyzed. If we don't have that sample, it's very difficult for us to know how much phosphorus, potassium, calcium, magnesium are in. We will run these tests in our labs in Nashville. So for a $15 fee, this is our basic plus analysis. The interpretation of these results is based on years and years of on-farm and on-station research across Tennessee. And we're always going to just recommend how much fertilizer is sufficient to produce a yield response. This is the type of graphs you get from many, many years of soil fertility trials. This is a response of cotton to different levels of potassium in the soil. And our recommendations are based on the probability of a yield response. So you can see our probability is it's very high in the lower end of the scale, then narrows out and then flattens off at the top. So quickly, as we start to wind up this particular talk about soils and soil health. This is what we're going to be talking about the rest of the session here. The United States Department of Agriculture defines soil health as the continued capacity of a soil to function as a vital living ecosystem that sustains plants, animals, and humans. And it's related to the chemistry of the soil, the physics of the soil. We've covered these topics already in this talk, as well as the biology. This is going to be covered in the next talks by Dr. De Bruin and Dr. Jagadama. And the biology is got here, there's more life in a teaspoon of soil than humans on Earth. So it's very, very rich. Just recall some of the things we talked about early on in this presentation, that soil health very much depends on the soil, and the soils that we see they come about because of the parent material they're formed from, the climate, the vegetation, the landscape position, and the age. So we don't really expect the health of the soil here in Tennessee to be the same as the health of the soil, for example, in Arizona, or the health of the soil in Canada. And I will leave you with this graph, this map of the different types of soils. It should come as no surprise. Soils that are produced in similar areas with similar parent materials, similar climate, and similar vegetation tend to be similar, whereas those, for example, in the Midwest are also similar but quite different from ours. I'd like to thank you for your time here, and if you've got any questions, please do not hesitate to email me. This is my email address at the bottom. Thank you very much.